Here's our last example for scalar line integrals for these videos. A wire runs along a curve parameterized by xy, given by x equals square root 3 times 1 minus t squared, y equals t times 1 minus t squared. The square root 3 just makes the numbers work out nicer. For the interval from t equals -1 to 1, its density is either delta equals 1, constant density, or delta equals x. We're going to do two examples. Let's sketch the curve, find its mass, and find its center of mass. Regardless of density, the shape of the curve is the same. So let's plot some points. When t equals 0, or well, we should start when t equals -1. When t equals -1, x is 0 and y is also 0. So this curve starts at the origin when t equals -1. When t is in the middle, t equals 0, then x equals square root 3. And when t equals 0, y also equals 0. That's when t equals 0. Then at the end, when t equals 1, x is back to being 0, and y is also back to being 0 when we plug in t equals 1. So we're back here to t equals 1. Now, if we plot a few more points, like t equals plus or minus 0.5, we can see that this curve starts at the origin, loops over to the side, and loops back. Let's see what happens if t is plus or minus 0.5. Then t squared would be a quarter. This would be 3/4. We'd have root 3 times 3/4. So 3/4 of the way from the origin to root 3. So roughly around roughly here. Is 3/4 of root 3 greater or less than 1? If we squared it, 3/4 of root 3 squared would be 27/16. That's greater than 1. So the original number must have been greater than 1. So I guess 3/4 of the way is really on this side of 1. Okay, and what about y? When t is plus or minus 0.5, then we have plus or minus 0.5 times 1 minus 1/4. So in other words, we have plus or minus 3/8. Plus and minus 3/8, and somewhere around here is 3/4 of root 3. And that's what happens when t is minus 0.5 or plus 0.5. All right, so this is maybe not a super accurate drawing, not to scale or anything, but it's a sort of teardrop shaped kind of loop, something like that. It might be interesting to try to find the correct lowest and highest points on this curve. I've drawn them as being at the 0.5 marks. I don't know if that's right. That would be fun to figure out. Well, so we've got a sketch of this curve. Where do you think the center of mass is going to be located? Somewhere inside the loop, for sure, right? When it has constant density 1, it's probably somewhere right in the middle, right about halfway from one end to the other, more or less. This curve is wider on the right, so it might be pulled a little bit to the right of the midpoint, just because of the curve being wider on that side and pointier on the left. When the density is x, that means that the curve or the wire is very light near the origin and heavier on the right-hand side. So I would expect that center of mass to be pulled even more so to that side. And this curve is symmetric, top and bottom, and these densities don't vary based on y. So the upper mass is going to exactly balance out against the lower mass. They have the same density and the same shape. So I'm going to expect that the center of mass is located on the x-axis. Let's see what we find out when we work it out for real. First, let's find the mass. The mass, if we use our first density, density 1, it would just be the integral for t equals -1 to 1 of that density times ds. I should have worked out ds before I started writing this down. We're going to write ds a bunch of times. So if that given parameterization is our r of t, then our prime of t is square root 3 times -2t, and then 1 minus 3t squared. And the magnitude of r prime of t is the square root. All right, when we square this component, we get 12t squared. And when we square this component, when we square it, we get 1 minus 6t squared plus 9t squared. We can combine the t squared terms. 1 plus 6t squared plus 9t squared to the fourth. I wrote 9t squared. I meant 9t to the fourth. Sorry about that. Right, when we have 1 minus 3t squared and we square that, we'll actually get 9t to the fourth. Sorry about that. All right, and so we might recognize this as being kind of the same thing, but with a plus instead of a minus. So sure enough, this is 1 plus 3t squared, and the square root cancels the squaring, and we just have 1 plus 3t squared. So when I said that this square root 3 was going to make the numbers work out nicer, this is what I meant. It makes this work out nicer. So ds is 1 plus 3t squared dt. And that's what goes into our mass, 1 plus 3t squared dt. Well, it's not too complicated of an integral. We should have t plus t cubed evaluated from -1 to 1. And with a little bit of arithmetic, that comes out to be 4. This wire has mass 4. what about the other density, density x? That was ds. Density x, but x is square root 3 times 1 minus t squared. Okay. Times 1 plus 3t squared dt. We don't need any fancy tricks this time, just a little bit of patience. So we'll multiply it out. FOIL with 1 plus 3t squared minus t squared minus 3t to the fourth dt. We might as well collect some terms. 1 plus 2t squared minus 3t to the fourth dt. And then integrate with the power rule. So root 3 times t plus 2/3 t cubed minus 3/5 t to the fifth from minus 1 to 1. And then now it's down to some fraction arithmetic. Root 3 times 1 plus 2/3 minus 3/5. That's when we plug in t equals 1. When we plug in t equals minus 1, we're going to get the exact opposite thing and then subtract that. So that's the same as adding a copy. So we have some fractions. We'll put it on a common denominator of 15. We have 15 plus 10/15 minus 9/15. So 16/15 times 2, 32/15 root 3. Okay, that's the mass of this wire if it has the density given by x. Now let's start trying to figure out our centers of mass. So what would be the x-coordinate of the center of mass in the first density with constant density 1? Well, we would take 1 over the mass that we found. We found mass 4 when we used this density 1. Integrate minus 1 to 1. Take x times the density. X is root 3, 1 minus t squared. That's x. The density is 1. And then we have ds. And perhaps you might recognize this integral. This integral is the same as the mass integral we just did. Same integral as m2. So for once, we don't have to work too hard. There is a 1/4 in front, but we already evaluated this integral. 8/15 root 3. 8/16 would be 1/2. 8/15 is a little bit more than a half. So this is a little bit more than a half of root 3. Does that line up with our expectations? Going from 0 to root 3, halfway in between would be half of root 3. We found that the center of mass was a little bit more than half of root 3. That does line up with our expectations because we thought this end is wider and there's more wire there. This left end is pointier and there's less wire there. Let's go on. What about the center of mass with the other density? Well, it would be 1 over the mass that we found times the integral from -1 to 1 times x, which is √3 1 minus t squared, times the density, which is also √3 1 minus t squared, times ds, 1 plus 3t squared dt. Right, here's x. This is the density, and this is ds. And you can imagine how we would do this. We would multiply out how the √3's group up and give us a 3. Then we have 1 minus t squared times 1 minus t squared times 1 plus 3t squared. It's not difficult, and it doesn't require any leaps of creativity or coming up with the right method. All it requires is a little bit of patience to multiply stuff out, or a computer. So let's just enter this one into a computer. I happen to have a Sage workbook open here. And we can enter this in. The integral we're interested in is the function, well, so we'll have 1 over 32/15 times square root of 3 as a factor in front. Now let's play it safe and put parentheses there. The integral that we want has a 3 because there was a square root of 3 times square root of 3. There's 1 minus t squared times 1 minus t squared again times 1 plus 3 t squared. And we're integrating with respect to the variable t, that's dt, and it's the interval from -1 to 1. I should say this is Sage. You can see it here, Sage Math 9.0 in the upper right corner. All right, Sage, what's that integral? Unexpected EOF. Okay, let's try again. The wrong command? No, I don't think so. Yeah, I tried this before. Let's see. Oh, I have a parenthesis in front of this 1 that I'm not closing. Got to look out for those parentheses. Name t is not defined. Okay, t equals variable. I'm not the biggest expert in Python and Sage, so I'm still learning. We had to tell Sage that t is a variable. We had to keep track of all our parentheses. And then this is the integral. Sage will take care of multiplying it out. We got 5/7 times square root of 3. 5/7 is more than a half. 1/2 would be 5/10, or 3.5 over 7. 5/7 is well over half. It's definitely more than 8/15. So, as expected, this density that was skewed to the right did pull our center of mass to the right. Let's quickly run through the y coordinates of the centers of mass. We had a pretty solid idea what to expect there. So let's just run through it quickly and see what happens. With the constant density 1, the y coordinate of the center of mass is 1 over the mass times the integral from -1 to 1 times y, which is t, times 1 minus t squared times 1 plus 3t squared dt. And well, let me, just to be clear, I'll throw in a times 1 here. So t times 1 minus t squared is y. 1 is the density, and this extra part is the ds. So we want to integrate that. This one we can do by hand, just to help see what's happening. We already went through the experience of multiplying out 1 minus t squared times 1 plus 3t squared. That multiplication was carried out here, and we got 1 plus 2t squared minus 3t to the fourth. So this time we're going to get 1/4, integral -1 to 1. We have an extra factor of t, so t plus 2t cubed minus 3t to the fifth dt. Antiderivative is 1/2 t squared plus 2/4 t to the fourth minus 3/6 t to the sixth. And we're going from t equals -1 to 1. So we have, when we plug in 1, we get 1/2 plus 1/2, or minus 1/2. When we plug in t equals -1, they all get squared out. You get 1/2 plus 1/2 minus 1/2. The same thing. That was supposed to say 1/2. And this all cancels out, and we get 0. The y coordinate here is 0. Taking a step back, you might notice one of the patterns of integrals. This is an odd function, meaning that if you negate the input, the output will also get negated. If we plug in minus t, this function takes on the opposite value. So this is an odd function on a symmetric interval. So the values on the right cancel the values on the left. And it lines up with our expectations that y coordinate is 0. For the last one, the y coordinate with the second density function would be 1 over the mass, integral t equals -1 to 1. The y coordinate is still t times 1 minus t squared. That's still y. What changes here is the density. We have √3 times 1 minus t squared, because in this example, the density is given by x. And then finally, the ds, 1 plus 3t squared dt. That's ds. No tricks are needed here. Just multiply everything out and integrate it. you might already be able to see that we're going to have an odd function without needing to actually carry out the multiplication. But just for fun, let's type it into Sage and let Sage do all the work. So the integral that we want to evaluate, I'll use t as a variable again, and we have 1 over the same mass and what we want to integrate is pretty similar. This time I'm going to have t times 1 minus t squared times 1 minus t squared again times 1 plus 3t squared. And t is going on the same interval from -1 to 1. Let's see if we get 0. Okay, here we go. 0. Yeah, no surprise. All right, that has been a conceptual explanation of where scalar line integrals come from and why they are that way, and some examples centered on finding total mass and finding the center of mass. In 3 dimensions, it would work similarly. Our r of t would have an x, a y, and a z component, but all the ideas are the same. If it wasn't mass, if it was something else like electrical charge, you could still use a scalar line integral to find the total electric charge along that path, or the total of anything you want. Scalar line integrals, they're pretty flexible, pretty useful. Well, that's it. Thanks for watching. Bye.